All right, so we're rolling. So what we're going to do today is we're going to talk about diffusion and equilibrium. We started this last time where we put the sodium chloride crystal in the bottom of the beaker and imagined how the thermal energy of the water molecules bouncing around would then chip off sodium ions and chloride ions, have a shell of hydration around those ions, and put those ions into solution in water. The main ideas we're trying to drive home with that were first the ideas of ion solubility because of the dipole moments on water. And secondly, we're trying to drive home the idea that those water molecules having a certain amount of thermal energy would bounce against the ions and disperse them in the water column. We'll bring that up again today, but now we're going to change the story just a little bit. And we'll first talk about ion diffusion in a water column, but now we're going to lay out a water column separated from another water column. What we're going to do is we're going to put a sodium chloride crystal in our thought experiment into a water column and separate that volume of water from a neighboring volume of water by a barrier. So of course, nothing can go through the barrier. But then what we'll do is we're going to put ion selective channels, or ion selective holes, if you will, in the barrier. And imagine what's going to happen. These ions are going to bounce against the barrier, but now and again an ion will find a pathway, an open channel across the barrier, and move from where it's in high concentration to where it's in lower concentration. And this process of randomly bouncing against the wall, randomly finding a way across the wall and going to the other side will continue until the probability of moving from one chamber to the other is equal to the probability of moving from the other to the one, and we'll draw that out. That will be the idea of equilibrium. Then we're going to change the story slightly differently. We're going to have the same thought experiment. We're going to set it up in the same fashion. We're going to put 0.1 molar sodium chloride on one side of the barrier and pure water on the other side of the barrier. But where in the first case we put in the barrier, across the barrier, through the barrier, ion selective channels, we're now going to have no ion channels in this barrier. Instead, we're going to have a specialized channel that's selective for water called an aquaporin. So now we're going to set up two chambers, one with pure water and one with a sodium chloride solution. But now the ions can't move. There are no pathways for ions. But there will be pathways for water, and we'll then think about the idea, the concept of water concentration. Water concentration being higher in the volume with pure water than in the volume that has sodium and chloride ions added. So now, again, we have a concentration difference. And that concentration difference now will allow water to move from where it's in higher concentration to where it's in lower concentration. Because the sodium and chloride ions are in the other chamber and will become diluted but never go to zero, there's always a movement, a higher concentration of water on the right-hand side than on the left-hand side. We get constant movement of water down its concentration gradient. And we'll talk a little bit about that. Once we've come through these concepts of ions in water and the movement of water, then we're going to move off into another extreme. The other extreme is being hydrophobic. And we're going to try to lay out the idea of contrasting hydrophobic with hydrophilic. Up to this point, we're talking about ions in water, so we're accentuating the idea of hydrophilic. But hydrophobic means water-fearing. And these are molecules that don't easily go into solution in water. And perhaps the best example, the most extreme example of hydrophobic molecules are lipids. Lipids could be animal fat, or the way we'll talk about them in our thought experiment is vegetable oil. We all know intuitively from everyday life, we know if we put vegetable oil into water, it doesn't go into solution. You can shake and shake and shake that carafe when you're making a salad dressing, and if you put it on the shelf, that olive oil will come out of solution because it's hydrophobic. The lipids, because they're uncharged, do not easily go into solution in water. To understand why that is, we need to walk through a little bit of chemistry. And the chemistry is to generate a triglyceride molecule. And there's even some meaning in the term triglyceride. The tri refers to the fact that there'll be 3 fatty acid molecules covalently linked to a glycerol. The glycerol will be a 3-carbon alcohol, and we'll use the 3 alcohols on the glycerol to form an ester bond to link to the fatty acids, and we'll walk our way through that. Now, the fatty acids themselves are hydrophobic. The glycerol is reasonably soluble in water because of those 3 alcohol groups. But once we have linked the fatty acids covalently through something known as an ester bond to the glycerol molecule, that molecule with its glycerol and the 3 fatty acids, that molecule has all of its electrons evenly shared. There are no regions of charge, a little bit perhaps on the double bonded oxygen, but almost no regions of polar or charged areas in that molecule. That lack of charge has meaning because it's the lack of charge which prevents the lipid molecule, the triglyceride, from easily going into solution in water. But then what we'll talk about is something called an amphipathic molecule. There's meaning in this term as well. Amphi meaning both, pathic meaning feeling. So these are molecules that live in both worlds. They have the capacity to both interact in a hydrophobic world and in a hydrophilic world. We're going to find that the classic amphipathic molecule is something known as a phospholipid. We're going to use the 3-carbon structure of the glycerol linked through its ester bonds to the fatty acids to begin the concept of a phospholipid. Because in a phospholipid, we're going to have 2 fatty acid side chains that are hydrophobic, but there's going to be a head group on the phospholipid which is hydrophilic. So now we're going to draw a molecule which has both hydrophobic and hydrophilic characteristics. And if there's time, we'll think about how we can sprinkle these phospholipids onto water, how they interact with water. And they're going to interact with water in such a way that their charged head groups will face the dipole moments of water, but their hydrophobic tails will turn away. And then we're going to imagine dunking these molecules underwater. Because now we have a hydrophilic region and a hydrophobic region. How might these molecules orient themselves underwater? Well, the tails are going to turn away from the dipole moments on water and try to aggregate one with another. And that's what happens in a micelle. The micelles are simply phosphate head groups facing outward, tails facing inward. The problem with a micelle in water is it just isn't very stable. All you need to do is get 1 or 2 molecules of water in among the fatty acid side chains and it blows up. So it's extremely unstable. So then we have to think about how to make these phospholipids stable in a water environment. The first way we'll do that is to generate something known as a liposome. And a liposome, the fundamental characteristic of a liposome is the phospholipids will be organized into a lipid bilayer. The phospholipids will be formed into 2 layers. One layer will have the phosphate head groups facing the water on the outside. The other will have the phosphate head groups facing the water on the inside, and we'll walk our way through that. And we'll then extend the idea of a liposome to a planar bilayer, and the planar bilayer is the basic structure that we find now for a cell, and we'll then incorporate that phospholipid bilayer into a biological membrane. But let's start here with the ideas that we had yesterday. So where this is simply a beaker. Now, what's different from the drawing we had on the board yesterday is we're now going to divide the beaker into 2 equal chambers. And we're going to fill both chambers up with water. On this side, we're going to start as we did yesterday with a sodium chloride crystal. And we said yesterday that we took precisely 5.84 grams of sodium chloride. Now you remember that there are 58.4 grams per mole for sodium chloride. So that means this is 1/10 of a mole. And if we put this into 1 liter, now we have a 0.1 molar sodium chloride solution. And we said yesterday, since these ions in the sodium chloride crystal completely dissociate, that means we're going to have 0.1 moles of sodium ion and 0.1 moles of chloride ion. And where we left off was the idea of the thermal activity, the thermal agitation of the water molecules bouncing around here in this chamber. would now strike the sodium chloride crystal and effectively chip off one ion at a time from the sodium chloride crystal. That the sodium ions then would associate with the negative end, the negative dipole moment on water, and the chloride ions would interact with the positive end of the dipole moment on water. But we would now have each of these ions surrounded by a shell of hydration. And those ions now, because of the thermal activity of the water, are bouncing around randomly. They're moving off in random directions. They'll move for a while, they'll strike another water molecule or series of water molecules, and they'll take another direction. So we can think about the idea here of a random walk of sodium ions and chloride ions. It's a random walk in such a way that eventually, wherever we look in this volume, we're going to find 0.1 molar sodium and chloride ions. 0.1 moles of sodium ions and 0.1 moles of chloride ions, wherever we look, because these ions have now become randomly distributed, and they've become randomly distributed because the water molecules have chipped off one ion at a time and put them into solution. And they go into solution because of the water characteristics, the dipole moments on water, and the hydrophilic nature of these highly charged sodium and chloride ions. But what we're trying to think about here is the idea of equilibrium. And we reach equilibrium when the ions are evenly distributed. Perhaps, in a real-world sense, the easiest way to think about this is to imagine that right in the middle of the room here, we would open a bottle of perfume. And those perfume molecules are volatile. They leave the volume of perfume and they go out into the air. And the air molecules then bounce against those perfume molecules, and they bounce them here and there, so that initially, when we first open up the perfume bottle, the people right in the center of the room, right around the perfume bottle, would smell the perfume. But given enough time, those molecules of perfume will be bounced about, be buffeted about by the air molecules, and eventually those perfume molecules will be evenly distributed throughout the room, so that people in the corners over time will eventually be able to smell the perfume molecules. It's the same idea here, but rather than having perfume, we have sodium chloride. The sodium, rather than having the perfume come out of the bottle, sodium ions and chloride ions are coming off the crystal and going out into the water volume and being buffeted about until wherever we look in the volume, we have the same concentration of sodium ions and chloride ions. We have come to equilibrium. Well, let's extend that idea a little bit farther. So imagine now we have divided this beaker into two chambers. The left-hand chamber has sodium chloride at 100 millimolar in it, and the right-hand chamber contains only water. Now, as long as this orange barrier is impervious, as long as there are no holes in the orange barrier, nothing's going to change. But now let's imagine in that orange barrier, we add in green some chloride selective channels. And in purple, we add an equal number of sodium selective channels. Now, if we think about the ions as being ping pong balls, imagine the ping pong balls bouncing around in here. And now and again, they bounce against the wall. Most of the time when the ping pong ball strikes the wall, it bounces back. But now and again, one of the sodium ping pong balls will strike the wall in just the right orientation so that it hits one of these openings. And it will now move from this chamber through the channel into the pure water. Similarly, the chloride ions will do the same thing. The chloride ions will be bouncing around in here, bouncing against the walls. And now and again, they'll strike the hole just right and move from the left-hand compartment to the right compartment. Now, when you think about this, there are trillions upon trillions upon trillions of these ions in this chamber. And now we only have 2 on the other side. So the probability of the ion moving from the right to the left is precious small. But the probability of the ions continuing to move left to right is pretty high. And so this action will continue. The ions will bounce against the wall. Occasionally they'll find a way across and they'll move into the other compartment. Because there are fewer of them in this compartment than this compartment, they're not likely to move right to left. But now over time, as the number of ions starts to approach here, 50 millimoles of sodium ion and 50 millimoles of chloride ion, then once we've reduced the concentrations in this chamber, we've now increased the concentration here to 50 millimoles of chloride and 50 millimoles of sodium. We've now reached equilibrium. So under these circumstances, using the millimolar designation as just a proxy for the number of ions, you can see that they're the same number of ions in this chamber as there are ions in this chamber. Since the numbers are the same, the probability of a chloride or sodium ion moving right to left is the same as moving left to right, and we have reached equilibrium. So we've simply reached an equilibrium, saying that the probability of the ions moving from this region to this region is the same as the probability of moving from right to left, because we simply have the same number of ions in both chambers. It's that simple. And that's the idea of an equilibrium. As a rule of thumb, you can look at these and say, molecules will move from a region of higher concentration to a region of lower concentration. They move from where they are to where they're not. We're going to see this pattern over and over again. This idea of ions moving down a concentration gradient is going to be essential for understanding how nerve cells work. It's going to be essential for understanding how muscle cells work. It's going to be essential for understanding how the kidneys work. This idea of moving from high to low is going to be repeated over and over again. So this idea of coming to equilibrium, moving down a concentration gradient, is a fundamental idea in all of biology. So any questions on that? Yes?
When it says 0.1 molar NaCl, is that saying that not all the NaCl is dissociated?
So this is a question. The question here is about the dissociation of sodium and chloride. And the way we've drawn this up is we've said that this is 5.84 grams of sodium chloride in this chamber. So that means this is 0.1 moles of sodium and chloride. But this sodium and chloride at 1.1 moles will completely dissociate into chloride ions and sodium ions. They come apart completely. Now, if you get into the physical chemistry of this, depending on how high the concentration is, they don't completely dissociate. But for our purposes here, they've come apart completely. So because they've come apart completely, they'll generate 100 millimoles of sodium ion and, chloride ion, and 100 millimoles of sodium ion. Because they've come apart completely. From 100 millimolar sodium chloride, you get 100 millimoles of sodium ion and 100 millimoles of chloride ion. Anything else? So now, over here, we're going to change the story just a little bit, but we're going to have the same drawing. So we'll start with the beaker. We'll, again, place in the middle of the beaker this barrier. On the right-hand side of the barrier, we'll have pure water. On the left-hand side of the barrier, we're going to, over here, have 100 millimolar sodium chloride. So we have our sodium ions and our chloride ions distributed randomly in here. Now, again, as long as this is an impervious barrier, nothing moves. But let's now imagine putting holes across this barrier. But these are going to be a special kind of hole. These holes are now water selective channels. Now, in biology, the water selective channels have a name. They're called aquaporins. So where in this example, we had pathways for ions to move, but no pathways for water. We're now going to flip that idea on its head over here. Over here, we have no pathways for ions, but we have pathways for water. And what we have to think about is that we have the same volume of water on the right-hand side as we have water on the left-hand side. But what you have to imagine in your mind's eye on this side is that the sodium ions and the chloride ions are taking up some room. They're taking up some space. And because they're taking up some space, they have excluded a volume from which water can occupy. We simply have less water here because the sodium and chloride ions are taking up some of the space, some of the volume. That tells us then that the concentration of water over here is as opposed to here. The water concentration on the right-hand side is going to be higher than on the left-hand side, simply because we have less water over here because some of the volume of this compartment is taken up by sodium and chloride ions. That tells us now we have a higher concentration of water here than here. So we can write this out as saying the H2O concentration is greater in the right-hand compartment than the left. So, from what we've talked about over here, what's the direction of movement of water? It's got to go right to left. It moves from a region of higher concentration into lower concentration. So where we were emphasizing over here the difference in concentration of ions, now we're simply turning the argument on its head and talking about a difference in the concentration of water. Water's higher here than here. Water's going to move down its concentration gradient. This process of water moving down its concentration gradient has a name. The movement of water down its concentration gradient is known as osmosis. Now, I want to emphasize the point here that this really is nothing more than a difference in the water concentration and the use of water selective channels. Now, in many cases, when we talk about this, we talk about a higher concentration of ion on one side than the other. And we talk about the water being drawn from the region where there's pure water to the region where there's ions. But it really isn't a drawing. There's no force to pull the water in that direction. It's simply the random walk of the water molecules bouncing against the barrier, and the water molecules bouncing against the barrier are more likely, because there's simply more of them on the right side than the left side, to move from right to left. It's that simple. Yes?
So the selective channels aren't necessarily pulling the water to it, they're just allowing water to get through.
You can think of so the question is, what is the function of those channels? They're just open holes. You can think of them as holes in the wall. Now they're small holes, so it's not completely a sieve, but we're trying to think about a fairly low probability of a water molecule striking that hole just right so it zips through to the other side. And as long as we have more water on this side than this side, these water molecules are going to be more likely to move right to left than left to right. Yes?
But because they're water selective channels, they won't let the sodium and chloride ions go.
So the question is, are you saying that because these are water selective channels, they don't allow the ions to move? That's absolutely right. These are only selective for water molecules.
Will the water level go up on the other side?
So the question is, what's going to happen to the water level on the other side? And the answer is yes. What will happen as the water is moving from right to left, this water column is going to get higher and higher. What the question shows is that there's always some sodium and chloride here. There's always pure water here, so there's always a gradient. So water's always going to move. And so what happens is this water column gets higher and higher and higher. And for those of you who had some botany will recognize this. This is the way the water column rises in a plant. So if you look at a tree outside during the summer, not so much this time of year, but if you look at a tree during the summer, what it's doing is it's drawing water from the soil into its roots by an osmotic gradient. And then the water is moving from cell to cell by an osmotic gradient, pulling the water out of the soil and moving it up through the water vascular channels of the tree. You can get water up, I think it's about to 60 feet using this trick. But there's only so far you can go, because what happens is you get a column of water such that this column of water has mass. So eventually you get such a height of a water column that there's a downward force here. There's a gravitational push on the water and a pull so that you eventually get a hydrostatic pressure. Get a hydrostatic pressure equal to the osmotic pressure. So in this case, we reach an equilibrium because we now have the probability of water moving left to right simply because of the mechanical force, the hydrostatic pressure of that column of water. So we do reach an equilibrium. Now, as an aside, this is limited in the height you can draw the water. But we know there's some trees that actually get taller than the limit on this hydrostatic pressure. But those trees, like redwoods, always grow in an environment where there's a constant mist. There's a mist that used to be coming off lakes, but I think it's all off oceans these days. And so those trees are now have been selected so that on their leaves they can collect water. And by collecting water in their leaves, they can circumvent this hydrostatic pressure problem and grow higher than the limit of the hydrostatic pressure, which normally limits the height of a typical tree. Just I think it's a nice example in biology of how we have these hydrostatic pressures, which limit the movement of water. We're going to run into osmotic and hydrostatic pressures again when we get to the kidney. Hydrostatic and osmotic pressures are really important in the kidney. They're important in parts of the vascular system, moving water and solutes in different directions. So any questions on that? So if not, what I'd like to do is move on from this idea where we're talking here about things that are extremely hydrophilic. These highly charged sodium and chloride ions are easily solubilized by water. And they're easily solubilized by water because the charge on the sodium ion and the chloride ion, these highly charged particles, easily interact with the dipole moments of water. So now we're going to go to the other extreme and talk about lipids as hydrophobic. Molecules. Now, lipids may be animal fat, or they may be vegetable oil. Regardless of whether they're animal fats or vegetable oil, they are all triglycerides. This term triglyceride has meaning. It means that there are 3 fatty acids. And there's 1 glycerol. Well, let's drill down into that a little bit and talk about the chemistry of the molecules we're dealing with here. We're going to start out here with glycerol. And glycerol is a 3-carbon alcohol. So there are these 3 carbons. You remember from your chemistry that carbons always have 4 bonds. So, but this, to make up the 4th bond here, this is to an oxygen, and the oxygen is linked to hydrogen. Now, this is a hydroxyl group. But in organic chemistry, when we see these hydroxyl groups, we say this is an alcohol. So that means this glycerol is a 3-carbon alcohol. It's reasonably soluble in water because these hydroxyls, these alcohols, are polar and will allow it to go into solution. But we can change the characteristic of this glycerol by doing another little bit of chemistry. Over here in orange, I'm going to start with something known as a fatty acid. The fatty acid starts here with a carbon with a double bonded oxygen, an OH, linked to a long string of carbons. Now, each of these carbons has 2, in most cases, hydrogens attached covalently. Now and again, there'll be a double bond and only 1 hydrogen on either side. But what I want you to recognize is that we have this great long chain of carbons, which can be 16, 18, 20, or 22 carbons long. But regardless of whether we're talking about 16, 18, 20, or 22, what's important is that wherever we look along the length of this fatty acid, that all of these electrons are being equally shared. There's no unequal sharing of electrons to provide any charge in this molecule. There may be a little bit out here in the double bonded oxygen. This will be a little bit polar, but that's a small portion of this great long chain. So we'll look at this molecule and say the electrons are equally shared. That's just another way of saying this molecule is uncharged. Because it's uncharged, it doesn't want to interact with water. So now, let's look at the chemistry of this. This hydroxyl now will be linked, we'll start out here, with the hydrogen. Now we have the carbon with a double bonded oxygen and an OH. This is said to be a carboxylic group, sometimes known as a carboxylic acid. That's the reason we have fatty acids, because of this carboxylic acid group. Now again, we'll just put a bunch of carbons out here. I won't go into all the details of the hydrogens and all that, but we have this long string of carbons. Now, biology doesn't do it quite in this fashion, but I want to show how we're going to make a lipid. Biology does it differently, but we're going to add some enzymatic magic here. And what we're going to do is we're going to take this hydrogen and this oxygen and form HOH. This is, of course, water. And when we remove that water molecule, we form a new bond. We form a new bond that goes from this oxygen to this carbonyl carbon. So we have a carbon, oxygen, carbon, double bonded oxygen. For those of you who had some organic chemistry, you'll immediately recognize this structure as an ester bond. An ester bond is defined as this organization of carbon, oxygen, carbon to a double bonded oxygen. So now we formed one ester bond between this number 1 carbon of the glycerol and the fatty acid side chain. And we can do this over and over again. We can go through the same pattern, where now we have this bond to the carbonyl carbon. And in the third case, again, an ester bond to the carbon double bonded oxygen with this great long chain. Now, wherever you look in this molecule, there is no charge. A better way of saying this is the charge is evenly distributed. Because of the even distribution in charge, these molecules don't easily go into solution. And we know this intuitively. If you go home at noon today, 1 o'clock, and decide you're going to have lunch, and decide that you would like to have for lunch a salad, and you're going to make yourself a salad dressing. Well, you know what you're going to do. You're going to get out what's fundamentally a beaker. We'll call it a carafe. You're going to put a little bit of olive oil in that carafe, and then you're going to fill the carafe with water and maybe add a little bit of vinegar, but vinegar is just in a water solution. So effectively, imagine we have this carafe. In the bottom of the carafe, we put olive oil. You could equally use canola oil, some other vegetable oil. And then on top of that, we pour water and perhaps some flavorings with vinegar. And then in the process of making a salad dressing, what you'll do is you'll take that carafe, you'll put a cap on it, and you'll shake it. You'll shake it and you'll shake it and you'll shake it, trying to get the olive oil to go into solution in the water. But we all know what's going to happen. We know that after we shake this carafe, that the olive oil in tiny droplets will be distributed throughout the water column. So these are oil droplets. But try as we might, as we shake and shake and shake that carafe, if we take the carafe and we now place it on the table or on the counter and let it sit for 20 minutes or so, you know what's going to happen. The carafe is now going to have a layer of oil on the top, floating on the water. Again, this is just an everyday example of how these hydrophobic, oil molecules would be happier assembling one with another than interacting with the water. Because of their lack of charge, they're going to accumulate one with the other, and because they're of a lower density than the water, they'll float to the top. We know this intuitively, but this is simply explained now by what we know from yesterday's lecture and today, that we have highly charged dipoles on the water that don't easily interact with the uncharged triglycerides. So the oil does not easily go into solution in the water and will float out on the surface. So any questions to there? Yes? Because I put it in the bottom first. So we could do it the other way around. I'm not sure how you make your salad dressings. But you could put the water in first, then pour the oil on top, and then you shake it. But it's not going to go into solution any better. So, sure. Anything else? Yes? So if you pour the water in first, then the olive oil still comes to the top. But the reason it comes to the top is simply that it's less dense than the water. The water per milliliter is heavier than the oil, so the oil floats to the top. Well, the next thing I want to talk about is to move on from these extremely hydrophobic molecules and begin thinking about how we can modify those molecules so that they are more hydrophilic. So we'll take this panel and we're going to label it as phospholipids as amphipathic molecules. And what we mean by that is an amphipathic molecule, coming out of the Greek meaning both feeling, an amphipathic molecule has characteristics which allow it to interact both with an aqueous environment and with a lipid environment. So in order to see how that's going to work, to see how these molecules are going to function, we have to spend a little bit of time on the chemistry. And we're going to basically take a triglyceride and modify it just a little bit. We'll talk about phospholipids, as amphipathic molecules. Again, amphi meaning both, pathic meaning feeling. To generate these phospholipids, we're going to start out with the same pattern we had before. We're going to start out with a 3-carbon alcohol. This is going to be the glycerol. Now, 2 of the carbons, these first 2 carbons, we're going to do just as we did before. We're going to take that carbon, link it through an ester bond to a double bonded oxygen to this great long chain of carbons. Again, forming an ester bond, carbon, oxygen, carbonyl, carbon, this great long chain of carbons. But now on the number 3 carbon, and the 3rd carbon, we're going to do something a little bit different. Rather than linking it to this great long fatty acid side chain where there's no charge, we're now going to make a different linkage. We're going to take this, let's switch this around so I can work with it. Hydrogen, hydrogen. Now we're going to have a hydrogen here and an oxygen. There's the OH. But now this oxygen, rather than being linked through this ester bond to this long fatty acid side chain, this oxygen is now going to be linked to a phosphorus. Phosphorus has a double bonded oxygen and has an oxygen with a negative charge. Then this phosphorus has an oxygen here, so we go, sorry, should have gotten rid of that hydroxide. When we generate this, we get rid of the hydrogen. So we have carbon, oxygen, phosphorus, oxygen. So we have replaced that hydrogen, which was on the hydroxyl, and formed this covalent linkage, carbon, oxygen, phosphorus. Now this oxygen out here is now going to be linked, I'm just going to put a box in here, to another structure. This structure could be an ethanolamine, it could be a serine, or it could be a choline. Let's take first the ethanolamine. The ethanolamine is a 2-carbon structure. So the oxygen is going to be now linked to a carbon, another carbon, there'll be the hydrogens here. But now out here on this carbon, there's going to be a link to a nitrogen, and the nitrogen will have 2 hydrogens on it. At biological pHs, this is charged enough that it will take on another hydrogen ion, so it's said to be protonated. Regardless of how we get there, what I want you to recognize is that out here, this structure, known as the phosphate head group, the phosphate head group is charged. So now we have this molecule. The 2 fatty acid side chains back here are uncharged. That is, they're hydrophobic. But this head group out here, with its charge on the phosphate and its charge particularly on this ammonia, this NH2, this is a charged head group. And whether we're talking about choline, which has three CH3s out here to make a quaternary ammonium and make it charged, or whether we're talking about nitrogen on the serum charged, these are all charged head groups. Now we have this molecule that has both the characteristics of a lipid because it's hydrophobic at this end, but it's hydrophilic at this end. We use a kind of shorthand to describe these molecules, where we draw a circle and a couple of squiggles. This sort of two-handled lollipop is a phosphate head group with these two fatty acid side chains. Well, let's imagine some thought experiments where we can get those molecules to interact with water. So in this first experiment, I'll just use the carafe. In this thought experiment, now you can't really do this biologically, but I think it's a useful way to think about these molecules. So let's imagine we have this carafe. We won't have any olive oil in it. It's just a carafe of water. And then up here, this is going to be meant to be a salt shaker. And we've put in phospholipids. And in this thought experiment, you imagine we can now take the salt shaker and sprinkle onto the surface of water the phospholipids. Of course, this is not possible to do, but when we think about it now, what I want you to think about is how these phospholipids are going to organize themselves and orient themselves in the water. Well, the phosphate head groups are going to be charged, and so they're going to interact with the dipole moments. Of the water. The water is charged, has a dipole moment. It's negatively charged at the oxygen end. So the positively charged phosphate head groups are going to interact with those water molecules. But the tails, the lowest thermodynamic state for the tails is not to interact with water, so the tails will turn round. So by sprinkling these phospholipids on the surface of water, we can think about the idea of the phosphate head groups facing the water, but the tails turning away. And we'll effectively get a monolayer here of phospholipids on the surface of the water. But that doesn't tell us very much about how these phospholipids can organize themselves below the surface of the water. It talks about how these phosphate head groups would orient themselves at the air-water interface, but it doesn't tell us much about what happens when we dunk these underwater. So let's imagine putting these phospholipids underwater. Well, one way we can get a reasonably stable thermodynamic state is to form something known as a micelle. In the micelle, the tails, the fatty acid tails, point inward, away from the water. And the heads face the water. Now, the problem with this, in the last few seconds here, the problem with this is that because these hydrophobic tails are pointing inward, all you have to have happen is if a water molecule sneaks by the heads and finds its way into this region around the tails, the whole thing blows up. So it's not very stable because these Hydrophobic tails don't want to interact with water. This is an unstable organization. What I'll leave you with is to think about how we can organize these phospholipids in such a way that they can be stable in water, and we'll come back to that idea tomorrow. Okay? No, I think they have two.